Welcome back to ChemDoctor, and in the previous video on gases we learned about the relationship between molar mass and the density of a gas. And what I'm going to do is I'll put that equation over here on the right so we can see what that looks like. And what we're going to do in this video is actually utilize this concept now to solve a problem. And you will want to see the previous video if you don't understand how to go from the ideal gas law to this form of the equation. All right, let me write the ideal gas law down here too. So we go from the ideal gas law, PV is equal to nRT, to this new form, which is pressure times molar mass is equal to the density of the gas times RT. So little d is the density. Remember that for the density of a gas, the units are going to be grams per liter as opposed to the density of a solid or a liquid, which is going to be grams per ml or grams per cubic centimeter. So you need to watch out for your units when you're dealing with the density of a gas, grams per liter. All right, and then molar mass is as we already know it, which is grams per mole. All right, so now what we're going to do is we're going to use this relationship to solve a problem. And perhaps the classic problem is one that combines utilizing the gas law to find a molar mass with empirical formula. So let's take a look and see what the challenge is here. So the question goes something like this. We've got an unknown gas in a container of some kind. We're told that that gas contains only carbon and hydrogen. So this is a chemical compound that is composed of only carbon and hydrogen. It's probably what we call an alkane. The compound has an empirical formula, which is CH2. All right, so the empirical formula, and I'm going to rewrite that down here so we can see it. And I abbreviate empirical formula EF, and it's equal to CH2. So remember, an empirical formula is a chemical formula which is in the lowest whole number ratio possible. The actual chemical formula will be some kind of multiple of this formula. All right, now what information do they give us in the problem? All right, they tell us that the density of the gas is 1.65 grams per liter. They tell us the temperature of the gas is 27 degrees centigrade and the pressure is 734 torr. They want us to determine the molar mass of the gas, and they want us to find the chemical formula, the actual chemical formula of the compound. So I'm going to go ahead and translate the information that we're given here down below here so it's more useful or immediately extractable for us. So let's see, the density is 1.65, and that's units of grams per liter. The temperature is equal to 27 degrees centigrade. Now remember, anytime that we're using the ideal gas law that has the gas constant R in it, and R is equal to 0.0821. Most importantly is for you to understand that the units on this constant are liters times atmospheres divided by mole times Kelvin. So my point is that the temperature was given to us in degrees centigrade and it needs to be in Kelvin. So what we're going to do is take the degrees centigrade and we add it to 273 to get the Kelvin temperature. So T Kelvin in this case is going to be 300 K. Now the pressure was given to us in torrs, and like the situation with temperature, in this case we need to be in atmospheres. So the conversion factor or the unit multiplier is the fact that 1 atm is equal to 760 torr. And just in case you're rusty on the temperature conversion, that was Kelvin is equal to whatever the degrees centigrade are plus 273. And degrees centigrade is the same thing as degrees Celsius. All right, so getting back to the problem, we need to change the torrs into atmospheres. So we're going to multiply 735 torr times 1 atmosphere over 760 torr. And you can see that the torrs cancel out. And we've solved for atmospheres, which will be 0.96. And then I carry the numbers out here without rounding. Because in a problem like this, when we go from the empirical formula to the actual chemical formula, we're going to be taking a ratio. And I want that ratio to be as close to a whole number as possible. So in a problem like this, essentially what I tell my students is rounding is death, so don't do it. You want to carry your numbers out and not round, so that when you take these ratios, you're as close to a whole number as possible. All right. So now that we've converted the various information we've been given to the correct units, now we can solve for the molar mass of the gas. So P times molar mass is equal to dirt, dRT, and we're going to divide both sides of this equation by the pressure. So the molar mass of the gas, of the empirical formula of the gas, essentially, well, okay, so this is actually going to give us the molar mass of the actual compound, all right, the actual compound itself. So molar mass will equal the density times RT over P. So now we can go ahead and plug in our values. So the density is 1.65 grams per liter. The R value, 0.0821, and I'm going to be careful not to be lazy and put in all my units. So it's going to be liters times atmosphere over mole times K. The temperature is 300 Kelvin. And we're dividing by the pressure, where we're going to keep all the numbers, so it's 0.965789 atmospheres. Now, you can see clearly that if we look at which units are canceling, my Kelvin cancels with Kelvin, my atmospheres with atmospheres, and liters here with liters here in the R constant, and that is going to leave us with grams over mole, which is what we're solving for. So the molar mass of the actual compound is equal to 42.079, right? So this is the molar mass of the actual chemical compound. Now, how do we find the chemical formula? So this is where we're going to bring together the empirical formula and the molar mass of the actual compound. So what we need to do is we need to know the molar mass of the empirical formula. So molar mass of EF is going to equal 14.026. Where did I get that number? All right, so the carbon, if you look on the periodic table, is 12.01, and on my periodic table, my hydrogens are worth 1.008, and there are two of them. So when you sum this together, you get the 14.026. So now what we're going to do is we're going to take that ratio I was talking about, and the ratio that we want is the molar mass of the actual compound, I'll abbreviate it this way, divided by the molar mass of the empirical formula, which is always going to be a smaller number, unless the two values are equal. And in that case, the empirical formula is the molecular formula. But in this case, you can see they're not equal. So the ratio is going to be 42.079 divided by 14.026. And what we get is 3 is our whole number. So again, the whole reason we're carrying numbers out is because this number that we're getting right here, if it's not a whole number and you've done major rounding where you haven't been careful, then this number right here, the ratio when you take it, is not going to be a whole number, and quite frankly, it's going to freak you out. So the bottom line is that you want to not round. That way, when you take this ratio, you will get a whole number or something really, really close. Like it would have been like 2.999, which is clearly 3. And now what we're going to do with this number is we're going to take it and we're going to multiply through the empirical formula. And that's going to give us the chemical formula of the actual compound. So here you're going to see that we get C3H6. And this would represent, therefore, the chemical formula of the actual unknown gas that we were charged with finding in the original problem. Okay, this is the classic type of molar mass density problem that you can get with a gas that combines two completely what appear to be two completely different concepts in chemistry. One that involves the determination of chemical formulas using empirical formulas and information regarding molar mass, and the ideal gas law and the properties of gases. All right, and with that, I'm going to go ahead and close the video.